Oh, I think it's on actually, screen. Okay. Hi, everyone. Thank you for coming to the EI seminar today. I'm really excited to welcome Jeannette Bohg to the seminar. So Jeannette is currently an assistant professor at Stanford, and she was also previously the group leader of the autonomous motion department at MPI until 2017. Before joining AMD in 2012, Jeannette was a PhD student at the Division of Robotics Perception and Learning at KTH in Stockholm. And she has received several early career awards, as well as Best Paper Awards, most notably in the 2019 Robotics and Autonomous Society Early Career Award and the 2020 Robotics Science and Systems Early Career Award. So I'm really excited to welcome Jeannette Bohg to give a talk here today.
Thank you. Yeah, hi everyone. Thank you for coming. I'm excited to be here. I had a great day so far talking with many of you. Yeah, it's very nice. I'm always lost in this building, but everyone shepherded me around, so that was good. All right, so yeah, so basically today I'm going to talk about scaling learning for long horizon manipulation tasks with language logic and YouTube. And so I've been really interested recently in long horizon planning. So it would really be wonderful if my research or the research in my lab enables robots to perform this long horizon planning, where the robot might be given like a high level goal, such as cooking a meal in this beautiful kitchen. And if you ask a robot to do that, it really needs to figure out the sequence of actions to achieve this goal. And what seems really infeasible in my mind to do here is to plan every joint motor command on this very low level to accomplish such a long horizon task, such as cooking a meal. It's really not very computational. It doesn't seem computationally feasible to do that. So when we think it's really helpful to abstract away low-level details of the environment, such as the exact poses of mesh geometries of the objects, and operate at the level of symbols instead, such as whether this pot, what's going on? Whether this pot is on the stove or not, or whether this microwave is closed, for example. So using symbols like this is called task planning, and it has roots in early AI. Where basically people study how a robot can be given the ability to reason through symbols and logical reasoning. And unfortunately, though, task planning by itself isn't really enough for robotics to perform tasks in the real world. So here's an example of where this may not really work, right? So let's say this robot is tasked to pick up a mug from the dishwasher and put it into the shelf. That's its goal. And a task planner that only operates on these symbols may come up with a simple sequence like that one that first picks up the mug and then places it in the cabinet. But you see that if the robot actually tries to execute that in the real world, it may very likely fail by just colliding with the gripper with this cabinet, right? And so we need some way to actually we need to pay actually attention in robotics to these geometric details at the lower level by, for example, doing some kind of motion planning to check if a task plan is actually geometrically feasible or not. And so if we do that, we might come up with a different solution where the robot actually picks up the mugs, places it first on the counter, regrasps it, and then places it in the cabinet without any of these errors, right? And so that really motivates this integrated loop where we have task planning at the top level that interacts in this loop with motion planning, which is typically called task and motion planning, which I'm sure many of you, I don't need to explain this to many of you. But yeah, so of course, this task and motion planning is a huge field, and here just two works, one from MIT, of course. These are really some state-of-the-art TAMP algorithms which can perform long horizon tasks, such as the ones you see, grabbing objects outside of the robot workspace, performing food operations in the kitchen, and so on. And these planners can really find very impressive solutions to these long horizon planning problems. But the catch with them is that they are still extremely computationally expensive. So the TAMP solution in this video here took several minutes to compute. And as a result, often these TAMP solutions that we see here, like these or also others, they're often limited to either simulated environments, like the one here on on the left, actually, now I'm thinking like coincidentally, both of them were done at MIT, right? Like this was when Mark was actually here at MIT. Yeah, and so basically, this one was, I think, demonstrated on a simulated environment only, or they are kind of like the small scale environments, right? So there are no moving objects or external disturbances. And we really wanted to think about, okay, how can we bring this interesting concept of layering the problem solving into symbolic and geometric levels and bring this to the real world and really scale it up without the robot having to pause maybe for several minutes to come up with a feasible temp plan, like once things have changed. And so the focus of this talk today, and this is going to be maybe potentially really cramped, so I hope it's not going to be too overwhelming, what I'm planning to talk about. But I really want to touch on each of these components that I think are really essential to bring a task and motion planning algorithm on a real robot and really scale it up. So often TAM planners are often kind of like confining themselves to these two layers, the task planner and the motion planner, but somehow it would be great to have reactive controllers as well that actually can react to immediately to when the world actually changes. And instead of having to go through this more expensive temp loop over there. Okay, so that's something we did a few years ago, where we wanted to bring temp out of simulation and apply to a dynamic real-world environment. Okay, so let's revisit this problem again that I think many of you are familiar with, where the robot needs to manipulate an object outside of its workspace. There are 4 objects on this table. There are 4 objects in this environment: a table, a large box, a small box, and an L-shaped hook. And if we want the robot to put the small box onto the large box, it actually has to come up with the solution, and that it has to pick up the hook and pull the box closer to actually accomplish this goal. And so the plan here that the task planner should come up with is to first pick up the hook, then pull with the hook the small box closer, place the hook on the table, pick up the small box, and then place it. And so that's the task plan, and then motion planning needs to find the geometric details, such as where to grasp the hook exactly, how close to pull the small box, and so on, so that we have a concrete trajectory that the robot can actually execute. Okay, so we built on, wait, was this actually video? Sorry, no. So we actually built on, sorry, I'm somehow lost with my slides right now. I'm sorry. What happened? Okay, so we built on this framework that Marc Toussaint did while he was actually here at MIT, that also built on earlier work that he's done, where he combined PDDL planning with nonlinear trajectory optimization. So this work was really interesting, but it does produce trajectories in joint space. And this is all totally fine. They are valid as long as nothing in the environment is changing and the perception and control are highly accurate. So if something changes in the environment, for example, the small box moving around, then the joint configuration for grasping is suddenly invalid that came out of this TAM planner, right? And so in this case, the robot would basically need to stop, replan everything, which takes several minutes. So that's what we wanted to avoid. And so the key contribution of this work that I wanted to briefly touch upon here, I actually don't want to talk about this in detail, is this TAM framework that actually optimizes trajectories over object-centric Cartesian frames that are relative to the objects rather than joint configurations of the robots. And the plan produced by this framework remain valid even if the objects are moving. And the plans themselves are executed by reactive controllers, just like an operational space controller that adapt to these changes in real time. And now that means that we can do task and motion planning now in dynamic environments where perception is inaccurate and control is imprecise. So here, basically, Toki, who is the main author of this paper, he's basically moving around these objects while the robot is actually executing this task and motion plan. And you see that it can continuously adjust to these changes. And it can also, as it turns out, actually produce, for some problems, plans in a much quicker way over these relative pose variables than if you were to optimize over joint configuration. So this is this Tower of Hanoi demo where you can basically have two different solutions or multiple solutions. And it also requires you to plan over this really long horizon, which our solution actually allows because there's some decoupling of the actions over this time horizon. Okay. So yeah, we also tried this on the real robot where we track the poses of the objects through some markers. So the perception is pretty basic over here. So that's not the main point, but there's certainly some noise that we see, and Tolki here is being annoying to the robot and doing the same disturbances that he did already on the objects in simulation to see how well this works actually also on the real world. Okay, so the tracking errors are actually quite significant, around like 1 centimeter. But the robot can still execute the TAM plan with local reactive controllers because of these relative pose variables. Okay, so I just wanted to motivate this, or basically show you what we want to achieve, this kind of reactive behavior that really adapts to the changes, to the dynamic changes in the environment. And so here the main idea was to have symbolic planning to create an action skeleton that translate into constrained motion optimization problem. And the algorithmic contribution in this work was this reformulation to optimize over these relative Cartesian frames. And the result you've seen was this task and motion planning in dynamic environments. Okay, so so now we can get around the computational cost of TAMP and apply it to dynamic and real-world environments. But with these relative pose variables, it can still take anywhere from a second to a minute to come up with the first TAMP plan. But once we have this initial plan, we can hand it over to reactive controllers, which will respond to small changes in the environment in real time. Okay, but while the reactive controllers are executing this plan, we would still want to continue running TAMP in the background and output new TAMP plans whenever we can and handle larger changes in the environment, such as when, for example, a block slips out of the hand, for example, and ends up back on the table and needs to be regressed. So we need a task planner to come up with a new plan to recover from such failures. But when you want to use a task planner in closed loop like this, you need a way to perceive actually the state of the environment, such as whether the block is in the hand or on the table. So we can pass this information to the task planner and replan accordingly. So this leads to the next work that I want to discuss that also allows even more reactive behavior. And this work is called Grounding Predicates Through Action, which addresses the difficulty of actually learning symbolic state perception systems. And so there is a name for this in computer vision. It's called visual relationship detections or scene graph generation. So here are some works that are dealing with this kind of problem. And so basically the vision community has worked on this problem of detecting these symbolic states. And the common approach is to collect a large database of images and then have mechanical Turk workers, for example, manually label whatever predicates they can think of in this particular image here, for example. And then you train a neural network classifier to basically predict them from images. The problem is that manually labeling these predicates is extremely expensive, and just one image can contain prohibitively many predicates that grows exponentially with the number of objects. And then the thing is, like, here are all the labels that are actually, or predicates that are actually still true in this image, but they're not actually annotated in the ground truth data set, right? So even these large data sets that are available, they are not completely densely labeled. Okay, so In this work, what we wanted to do is to propose a simpler way to obtain these labels. And specifically, we wanted to have a labeling that is relevant to robotics as well, and specifically to robotic manipulation. And rather than labeling predicates manually, our key idea is to label them automatically with symbolic actions. And symbolic actions, as defined in the PDDL domain, contain pre and post conditions, like this one, for example, that basically describe how an action changes the symbolic state of the world. So once you have this PDDL domain, you also have these pre and post conditions. So for example, with this action of putting an egg into a bowl, we know that before the action is performed, the egg has to be in the hand, and the egg won't be in the bowl. And after the action is performed, the egg is in the bowl and no longer in the hand. And just by knowing what the action performed in this video does to the symbolic state, allows us to automatically label these two video frames, in this video showing a person doing this action, label these with these 4 predicates, basically. Okay. So, okay, so that's the core idea here. And so now, how does that actually work of training a predicate classifier by exploiting this idea? So first, you have to acquire a data set of actions. That seems pretty expensive, but as a proof of concept, we actually use this data set called 20 billion something something. It's a large scale data set of 200,000 videos of humans performing 174 common manipulation actions. And each video is annotating with the action that is performed in this video. Yeah, and it's really the only label that we actually need here. So if you were to manually label the predicates in this video, like a back of the envelope computation would be that, you would need 690 days of work to actually do this. And let's not do that. So instead, let's take our idea where you automatically label predicates to actions. And that requires you to actually write down the pre and post conditions for all of these 174 different actions that we had. And so if you have an expert like Toki who wrote all of these, it took him kind of 4 days of work. Okay, so now you have these pre and post conditions to actually then automatically label this huge video data set. And now you can train the actual predicate classifiers you're interested in that are important for these particular actions. And so I'm not going to go into detail. We just took someone else's architecture for visual relationship detection and retrained this architecture on, or used it as the architecture for the predicate classifiers. So here I just want to show you some examples on this 20 billion something something data set. So in this example of closing the book, you can see that the network correctly identifies the book as open during the beginning and closed at the end. And here you have a little bit more complex example, poking the flashlight so that it falls over. And you can see that the network recognizes the transition from upright to not upright. It also identifies when the flashlight and the hands are actually touching, which is interesting. So one thing that is interesting is like in these videos, some of the ground truth labels that we generated from our idea, they may actually be fewer than those that we can then classify, right? There are some labels that we can still detect in these videos that carry over from other videos and from other actions that might actually be intuitively for us as people interesting to see here as well. Okay, so now how do we use this on a robot? Here's how we can use these predicate classifiers to do closed loop task planning on a real robot. So we take these 20 billion something something trained predicate classifiers directly to this robot environment. And we set up a task planning scenario where the goal is to clear the fruit off the table. So this is this, on the top here, you see the logical formula for that goal. And the task planner comes up with a sequence of actions that's to satisfy this goal. given the current symbolic state as inferred from these predicate classifiers. And so the predicate classifiers also predict the state in real time. And so the robot can respond to failures and replan immediately as well. And again, Toki being annoying to the robot, asking it to replan basically all the time. Okay, so this is not yet hooked up with this trajectory optimization that we've seen before, right? But that would be basically the idea that you have these motions also being adaptive to this. So here the motions were actually sort of hard-coded. Okay, so the summary of this work, so this was published at ICRA 22 and is grounding predicates through actions. And the main idea is to exploit that actions change the symbolic state of the environment in a known way and use it for cheap proposition labeling of video demonstrations. And there's there's like a framework for obtaining these partial state labels for video demonstration and training these predicate classifiers. And we get 37 predicate classifiers that are relevant to 172 different actions that were in this data set and can be used for closed loop task planning. Okay, so now we have, with this work, basically made it easier to train predicate classifier by drastically reducing the cost of data collection. And we also showed that it can be used for closed loop task planning in the real robot environment. And we actually haven't put these two together, but that would be really great to do, to have this really reactive system. Okay, so instead of actually doing the engineering work and putting this together, we were thinking like, all of this is really nice. But still, what we have to do is to write down, all this PDDL domain, like here, for example, for this hook environment. And then we have to actually, I haven't shown you this before, but this is basically the formulation for this object-centric Tam work, where we have to basically derive for every single motion or skill that we want to do, we have to derive the constraints for this optimization problem, which can be super tedious. And it's just not really easy to scale in that way. And so that's why we were thinking as a first step towards scaling this Tam System app, what if we try to replace the hand-designed reactive controllers with learned policies that don't require privileged information or full state information about the object meshes and poses and can operate on raw sensory data instead. And so for that, we actually really looked at essentially this way of using this data set that is annotated with language as a way to learn policies for many different tasks by having the robot basically watch YouTube videos if you want. Okay, so in this particular part of the talk, again, this is going to be more one of the high-level works I want to talk about to just paint for you the whole picture of how we designed this entire Tam system. So for this particular work, we wanted to endow our robot with the ability to acquire what we call here manipulation concepts, but you could also think of it as a multitask policy, if you want. That's just another word for it. And so this multitask policy can be seen as a mental representation of verbs in a sentence. And so what we wanted to achieve is that given an initial scene image here on the left, and given various instructions, such as put something behind something or put something into something, we want our robot to generate the motion trajectories that actually accomplish these particular instructions. And so to achieve this goal, we constructed an embedding space that associates task instructions in natural language and scene images with motion trajectories. And so constructing this embedding space has multiple benefits. First, of course, we can specify a manipulation task with natural language instructions instead of goal images, which is something that has been done at the time of this work a lot. And of course, describing the task in language is much simpler than providing a goal image. And second, we can obtain a multitask policy to represent diverse manipulation skills, such as open something or close something. And hopefully, by using natural language, we can hopefully also generalize and training on a diverse set of manipulation tasks, we can hopefully generalize to novel but similar instructions as well. Okay. So how do we train the robot to output trajectories to accomplish these tasks? We basically use learning from visual demonstrations, which allows us to avoid reward engineering or kinesthetic teaching or teleoperation, which are time consuming and very difficult to scale up to a large number of tasks. Okay, so what is the data that we use? We use, again, this 20 billion something something data set for the visual demonstrations. It contains 200K video clips with 174 different action classes. And each video clip is annotated with these task descriptions, such as putting something on the surface, moving something up, and so on. Okay, so this is what we want to use for learning. But of course, the first obvious problem here is that there is a really large domain gap between the human demonstration and a robot simulation. And there would even be a domain gap between, the human demonstrations and the robot doing it in the real world. So here you see 4 examples of closing something, but they're really quite different from this robot simulation. And so we need a visual demonstration method that can handle different backgrounds, different viewpoints, different objects, and so on. And so the way we address this large domain gap is by using a video activity classifier to evaluate robot trajectories. So that's really the core idea of this work. So this video activity classifier is trained to classify the action labels for the human demonstrations. It basically, for these 4 videos, for example, has to decide like, oh, this is showing close something. And so once we learned an activity classifier on all of these different actions on this data set, we can now use it as well to score the robot videos. So for example, for this robot simulation video, we would ask the same activity classifier to tell us, is this robot actually closing something? Yes or no? And so this score represents how confident the video classifier estimates the robot video to actually show this particular action that we are asking for, of closing something here in this case. And so the way we use that score is we use it as a reward in an RL algorithm to actually learn a policy for this action. And so, so what did we do? We actually tested this for 78 different tasks in simulation. We picked 78 different tasks of the 174, which were actually simulatable in PyBullet in this case. And you see there are like some really simple one, like pushing things around on the table, but also things like scooping up particles or rolling something up a slope, opening and closing drawers and so on. So these are all the different actions we used. And then, or we trained on with this idea that I just mentioned. And then here, I'm just going to show you kind of straightforward without showing you the architecture of what we actually did. Some examples of the multitask policy on a diverse set of tasks. So this is really one policy for 78 different tasks that take the first image as input and this instructions as input as well. And here's some more examples of this for some more tasks. And we also could show that we can generalize to novel instructions where the robot still does something reasonable. So these were kind of just like qualitative examples for this. Okay, so in this work that was called Concept of Robot, the main idea was to learn an embedding space for manipulation concepts that are indexed by natural language instructions. And the algorithmic contribution was this imitation learning framework from human video demonstration that used this activity classifier to provide reward to the method that actually learns the policy. And the result was this multitask policy that executes 78 different tasks indexed by natural language. Okay, so this was actually, at this time, this was 2020, this was also a huge number of different tasks. So these are not the secant task where it's like pick up an apple and pick up an orange. It's like different tasks. These were actually 78 different, actual different tasks. Okay, so yeah, so now we have a promising approach to actually scale up the number of primitives that we could plug into a TAM framework like this. Also some promising diversity of the number of objects that these primitives can handle. Now, okay, so there's still a lot of work to do there. For example, we never put this actually on a real robot. But let's just say for now, given a collection of learned policies, how can we sequence them together for long horizon tasks, right? So you see there's like now a gap between this motion planner and the learned policies. How do we close that one to actually use these? Okay, so this is really not, so basically we have now again this problem, right, of this robot here, for example, trying to pick up this cup and place it in the cabinet, and it has these learned policies available. How the problem is, like, if it was just gonna sequence these policies one after the other, it's not really gonna work, right? So this is just the example that you've already seen, where not checking what the task planner actually outputs and just sequencing the policies or executing the policies in sequence is not gonna work. Okay. So what do you do, right? So I think one particular approach that people have been trying is actually to learn this high-level sequencing policy in conjunction with the low-level skills. So maybe that is a good together. And there are a bunch of, these are just some recent examples that have actually done this. And the problem with using RL for long horizon planning, though, is that there's an infinitely large number, or there are infinitely many long horizon tasks, and therefore infinitely many action sequences, each with their own set of geometric dependencies between them. And so all of these have to be learned potentially by this long horizon RL policy. So really, if we want to generalize to all of these different long horizon tasks, we have to train on an extremely large number of possible combinations of these skills. And that seems really sample inefficient, or given how sample inefficient RL is, this really doesn't seem very practical for a large domain of many actions. And in fact, for like all of these works, except from the one from Danny Dries at the bottom, all of these papers handle exactly one long horizon task that can only generalize to different instances of the same long horizon task. But Danny's work actually achieves some generalization to other long horizon tasks, but it achieves it by requiring data that is generated from handcrafted policies. But actually, this is where we wanted to get away from handcrafting these policies, right? Okay, so what we try to do instead is we want to keep the task planning part. We don't want to learn it here, right? So let's not do RL. Because the strength of task planning is that it could immediately generalize to any long horizon task, as long as you have this PDL domain, for example, written out. It does that by reasoning about these pre and post conditions that you defined in this domain. So we want to take advantage of this generalization ability. And the task planner will tell us which actions to perform and in what order. And all that's missing is a way to do planning with the learned policy that handle the geometric constraints of this task. Okay, so what we propose instead here is, instead of doing long horizon RL, is a sampling-based trajectory optimization with policy value function to realize TAMP with learned policies. Okay, so So what exactly is the problem we are considering? So we basically assume that we are given a library of independently learned primitives or skills. So what we want to do is we want to have this composable set of skills that we can, a library basically that we can potentially also just extend. And all of these skills are trained on just the one skill that they're supposed to do: grasping, picking, pulling, placing, and things like that. And we assume, okay, we have this task planner that actually provides us with a sequence of primitives that basically comes from the symbolic planner. Okay, so let's go back to what the challenge here still is, right? So again, we have this example of you want to pick up a hook to actually bring an object that is outside of the workspace of this robot closer to the workspace. But the issue is that if you just execute the task planning sequence in order without taking any geometric dependencies into account, this particular example will fail, right? So in the first skill, the robot actually has to pick up the hook in a certain way so that the next action, the pulling of the yogurt with the hook, actually works, right? So here, it just picked up the hook in the middle, which is probably the most stable grasp, but then it doesn't have enough reach for the next action, right? So it really matters how a skill is executed in the beginning of the sequence for how whether the task will actually be achieved at all. Okay, so executing primitives in an order that should solve the task can fail due to these geometric dependencies between these actions. And so the task success really requires reasoning over these long-term dependencies between actions in a plan. Okay, so our core idea is to cast planning with learned primitives as a maximization problem over the probability of long horizon task success. And so this is basically this, here's just basically a cost function written down where we want to optimize the sequence of actions that we execute. And we basically show that this cost function is equivalent to the product of Q function for each primitive policy in a task plan. So the Q function, you can think of it as the expected return, right, from a given state and executing this particular action A in that sequence. Okay, so so intuitively what this means is that if earlier actions in the sequence are executed in a way that neglect downstream action dependencies, we might expect one of these downstream Q values to be low. And hence the overall planning objective J will be low, right, in this product. And so the way we solve this problem is with sampling-based planning to find the trajectory where the Q values for all the primitive policies in the long horizon tasks are basically high. And so let's look at how this exactly looks like. Basically, this planning with learned policies requires three key components: the primitive policies, the Q function, and dynamics models that predict future states at which the Q function will be evaluated. So this is what you see here. We have the manipulation primitives on the top, and we basically train each of these to do their particular task in these diverse environments with SAC. And then from that, we get this policy, the Q function, and a replay buffer. And from this replay buffer, we basically train the dynamics models. So that are basically collected over the course of training the policy. So one thing I want to mention here under point D is that we also use something called uncertainty quantification. And the reason for that is that when you train policies in isolation for just picking or just placing, then if you then plug them together for a long horizon task, this might bring you into a state space that the individual policies have never seen. And so the Q value is going to be really bad, or it's basically going to be garbage. And you want some way of actually noticing that. And so what we did here is we used something called SCOD, but you could also use ensemble method, for example, that we also found works quite well to understand whether a Q function at this particular state is actually valuable or not, or gives you something reasonable or not. If it doesn't, then the cost will be low. Will be high as well. Okay, so let's look again at some in comparison to prior work, which includes using model-based RL for basically orchestrating these low-level primitives, or a traditional Tam method like PDDL stream. And our work that we want to generalize to these arbitrary long horizon tasks. And so what we found is that basically that these RL tasks, as I already mentioned, they are limited to the training tasks, often to the long horizon training task, while traditional Tam methods, they actually generalize to arbitrary tasks as long as they have this domain. But then in terms of planning time, one is more efficient than the other. The scaling for the first version actually seems pretty unscalable. And for the middle method, for the traditional one, we found it really hard to scale up to so many different skills, like let's say 78 or 174, as we have in the something data set. So that's by having this modular library of primitives, this is what we are trying to address here. Okay, so here are some results. Actually, how am I doing on time? I kind of covered my clock, so 10 more minutes, great. I think that should work. Okay, so here are the evaluation domains, like the little environments that we actually looked at. So all of these have basically specific unique set of action dependencies that really deter long horizon success if you don't plan over this horizon and maybe do greedy execution. So let me show you how this looks like on a real robot. So here's this familiar hook reach task that you've already seen, right? And if you execute this in a greedy fashion, then things go terribly. And if we go to this domain here, this is the constrained packing domain. So here, our method has to plan locations on the rack so that it basically has space for all the different objects. And greedy execution results in a configuration of objects that's imperfect, and the placement policy doesn't really know how to handle. And here you have this rearrangement push, where the robot needs to pick up this yogurt in this case and place it back on the table in a way that enables pushing it under the rack. And you see, like for the greedy policy, it just places the yogurt somewhere random where basically the hook then has to collide with the robot and it doesn't work. Okay, so just to summarize this particular work, and I know I'm not even stopping for asking questions, but let me know if you have any questions. I'm happy to answer them in between. But essentially with this work that's going to be presented at ICAR this year, the problem that we try to solve is sequential manipulation, or basically optimizing a sequence of skills for a problem that actually contains geometric action dependencies. Prior work, especially this long horizon RL work, trains a set of primitives for solving specific long horizon tasks that don't necessarily generalize to other long horizon tasks. And our core idea was to train these primitives independently and solve long horizon tasks by maximizing this long horizon success. And so we could solve these tasks that actually the primitives were not specifically trained on. Okay, so I have like one more work to race through, but before I do that, I just wanted to maybe stop and ask if there are any questions so far on this. The last piece of work is where what box is left? What box is left? Now we're going to throw out the task planner, okay? And what is it going to be? It's going to be an LMM, because we don't want to, like, in the end, we don't want to sit down and define a PDL domain for 174 different actions, right? Well, for the 20 billion something data set has been done now, so you could reuse it, right? But there are many more actions for which we want to potentially do this. Okay, so we want to do this with LMMs, and we are probably all aware of this kind of cool new work that came out, right, that uses large language models and a library of skills to control the robot through these natural language instructions in different ways. And so SECAN on the left, it selects the best skill to execute by scoring available skills and select the ones with the highest scores. And they terminate when the done skill has the highest score. And there's a variation of this where in a monologue, it's called in a monologue, that is also adding intermediate feedback during execution. But it's a myopic work, it's a greedy work basically. And so code as policies here is also really interesting. It gives an instruction and generates entire Python programs, which call APIs to predefined skills like pick and place, for example. But of course, LMMs can produce arbitrarily bad garbage. So we want to find out before we ask the robot to do this, to execute this, right? And so what we focused on in this work is really, how can we verify that this task plan makes actually sense and is feasible? But one interesting advantage of using these LMMs is that in-context examples are much more user-friendly to provide as a prompt to this LMM than like this whole PDDL domain, right? Okay, but of course we lack some guarantees on the output. So that is what we wanted to address. We wanted to do task planning with LMMs, but wanted to understand, okay, how can we use LMMs to generate and verify these plans for tasks with complex geometric dependencies, such as this running example that we had here. Okay, let's talk about this system that we built. So we call it text to motion, and here are the given components. Again, we assume we have a library of skills, just like in this prior work called TAPS. And then we have a language model that hopefully replaces our task planner and gives us a sequence of skills that would be useful to achieve the goal specified in a natural language instruction. And we have a library of predicate classifiers. So something that visually perceives the world and decides like, oh, is an object on something or not? And so you could think of this as the work that I showed you before, the grounding predicates in actions that could provide, for example, a library of predicate classifiers. Okay, and so what's the objective? The objective is to generate a sequence of skills and then optimize them basically such that it satisfies a language instruction and deals with all of these geometric dependencies as well. Okay, so how does this algorithm that we came up with looks like? First, it actually generates a goal proposition by querying the LMM with the language instruction and the scene description. So that's the first thing that we need. We need some way to decide when we have actually achieved the instruction. And so this is what we do in this case. And as a second step, we generate a plan through beam search by iterating through the following steps. For each iteration in that plan, we query the LMM for a useful skill, which I will talk about in a second. And then we use TAPS, the system that you've seen before, to optimize the skill sequence up to the current planning iteration and to see if it's actually good enough. And then we select the skill of the set of skills that we ask the LMM to propose with the highest combined score that basically describes usefulness and feasibility. Feasibility, like in the TAPS work that you've seen before. And so we terminate the search when the goal that we generated in the first step is satisfied or the max depth is reached. Okay, so here's how this looks like. Okay, so I'm just going to run you through this algorithm. So here you first have the instruction from a user that asks, like, how would you put 2 primary colored boxes onto the rack? And so we assume you have a vision system that can actually detect the scene objects, all the boxes, the hook, the rack, and the table. And we also can, again, describe these predicates, these scene object relationships. So as a first step, we predict the goal. So given this instruction over there, we have to somehow figure out, like, oh, okay, what's a formal way to describe the goal that our plan needs to satisfy at the end. And so here, for this goal of putting 2 primary colored boxes onto the rack, you see the combinations combined by or that would be a correct task. Would be a correct solution to that instruction. Okay, so what do? We have the LMM to propose 5 top valid actions given this goal. We basically take all of this, put it into a prompt, and then ask the top 5 valid actions. So here it would be pick red, for example. Then we use log likelihood scores from the LMM to score this one. And we use tabs to actually tell us something about the feasibility, the expected success of this action just up to this planning iteration. And then what do? We actually use our dynamics model from tabs again to predict forward, okay, if we execute this action that is scored so well, what is the state actually going to be like, right? That's what we've done in tabs. We check if the goal is satisfied or not. It's not. And then we basically keep doing that, right? So we then, to the prompt, we always attach again, like, okay, what has actually been done? And then keep doing the scoring, use the dynamics model to predict forward how the geometric state evolves, check if the symbolic goal is satisfied or not. And we do that until either the goal is satisfied or we run out of max depth for the beam search. And so if this is successful, this would be the feasible plan, right, that this system came up with. Okay, so I think I'm probably out of time. So I have more slides on this, but I think I should probably, let me see. Skip a few of those. That is maybe something interesting, the prompt structure that contains basically the header with all the predicates and primitives, a few in-context examples, and then the final prompt that we basically give to the LMM at every step. Again, we use the usefulness is evaluated via these log props that we get from the LMM. And then the feasibility is basically tabs, right? So I'm not going to explain this one again because that's just what you've seen before. And then we evaluate this in these different domains where we have either a very long horizon task or we have lifted goals where the instruction isn't specified over concrete objects. So for example, you want 2 of the blocks on the rack, right? It doesn't matter which ones. And then we also have tasks where the full geometry of the environment is actually not explained. Okay, so how does that maybe look like? So here is some solution that the system came up with. How would you put 2 primary colored boxes onto the rack? It looks like this. And you see the familiar hook pull, so it resolves this geometric dependency. How does the LLM know you need to use the hook? So this is in a few in-context examples, right? So there are some in-context examples where I've seen like, oh, this is how hooks are used, right? So these are different. I see. But it doesn't do geometric. You haven't told the LLM. No. No, exactly. It's guessing, and then we're using this prior work called TAPS to check like with these learned primitives, oh, is that actually feasible in this geometric state, right? Because that one we perceive as well, but we don't give it to the LMM, we check that with that other system. Yeah. We represent it with like literally position. So here we don't use images as input. We literally assume we have a vision system that gives us like the poses of these objects, right? Yeah, so here are a few more. Here's maybe something interesting that's like a comparison to the baseline. So we basically compare to in a secant and in a monologue. And you can see again that that work is greedy, right, or myopic, so it can't actually resolve these dependencies if there are any. There's another baseline that I'm not explaining right now. Yeah, and I think maybe I'm just gonna show this last slide where that summarizes again all these works. Again, like one thing you may have noticed is in the end, we haven't put everything together, right? Like all of these pieces are still kind of floating independently of each other. And it would be cool if we were actually put them together. For example, in Tam with learned policies, we don't actually use the same policies that we learned in concept to robot, but it would be interesting to do that, right? So there's still like a disconnect there. Yeah, we haven't also integrated these grounding predicates through actions into this LMM, for example. So there are lots of like these pieces that actually connect the whole system together, still missing. I would say there's also a hodgepodge of vision modules, right? And like, how do you actually represent the state here? So that's like a big question to answer, which I find really interesting to look at. And of course, none of these systems work perfectly. So there are lots of limitations that I also have a slide on, and I didn't yet bring it up. So first I want to thank you for your attention, and I know we are out of time. But yeah, thanks a lot for coming.
Yeah, thanks, Jeannette, for the great talk. If people want to ask questions now, just feel free to ask.
So in the last meeting, an example, we had to tell which action is invisible or just the one.
Yeah, so we can say, given this Q function, right, in the dynamics function, we can predict forward like how good an action is or not, right? We train the individual policies that instantiate these different skills. We train them individually on just doing picking or pulling or something like that. And then we use the Q function and the dynamics function that we train on this to basically check if the plan from the LMM makes any sense at all, right? Like if it's feasible. Exactly. So the LMM, we did no training. We just took the DaVinci 3 version of GPT-3. So there was no additional planning there, learning there.
What I'm wondering is the primitives, right? So picnics are very general things, and place is a very general. This way, so the chances that you could actually combine work independent types of people, they could actually come together to achieve that. Well, do that unless you already anticipated which particular
right. Yeah. So what we do is we actually have a sampling-based planning method to optimize the sequence of actions together. So we sample the A's, which are the actions, and then plug them into the Q function given the current state, and just evaluate like, okay, what's the expected return here? And we do that sampling for many different actions A. And so if you're saying, I think if I understood you correctly, right, you can pick an object in many different ways, right, 6 degrees of freedom, and you can place it also in many different ways. And so how does this even like come together, right? And this is where the sampling part comes in, right? Like we sample many different ways to do picking, right? And then we evaluate it with the Q function, how good that picking actually is, predict forward what would happen if we actually execute this picking action, and then we sample again for the placing. Yeah, so, and that is the thing that we don't, right? Like, so sometimes, like, especially in the case of the LMM, it might suggest to you pick up the table, right? Which is not the good action here, and that we've also not trained our pick primitive on. So that would be where uncertainty quantification again helps, where we can, that gives us a tool to evaluate how good this Q function actually is at this current state of this action. Right, it gives you some garbage, right? Like, and how do you know? So we use an ensemble methods to actually get an idea of how good the quality of the Q function there is.
If I go out of
Yes. It might be really high, for example.
So you were hoping that.
Oh, it's approximated with a neural network, so it would definitely give me an answer, right? Because it's like continuous. Right. Right, right. Exactly, exactly. Yeah. Any other questions? Yeah.
I have a question about the, I think it's called the prompting for the
Yeah.
LLMs. So how broadly sort of apply it? So for example, if I didn't have like the book there, maybe I had like a garter break or something, which presumably robot could use.
Yeah.
Do you think the LLM can sort of generalize from a small set of prompts?
Yeah, that's an actually interesting experiment that we totally haven't done. But I think that I would say like probably this could actually work really well. And like in a different work, we actually explored that I haven't talked about at all is how from a few examples that are like personal to a user, is an LMM able to summarize these example into a broader category, right? So, and that category then might contain the rake, for example, right? Maybe it's, you know, hook or maybe a fork or something like that. And then if it generalizes those, maybe the category, the upper level one contains the rake. So that could potentially actually work really well, but, you know, we haven't tried.
So the information will be available through like the scene part.
Yeah.
Prompt, but maybe not through the previous example.
Right. Yes.
I have a question on the chat group. So, from correctly, you are using an approach network to estimate whether that thing is out. But there's also a question by the line of do that.
Yeah. So what we actually do is we have like one like joint state space over basically that we stack to where we stack together all the states according to all of these different skills, and then we convert into the individual state spaces for the different policies from there as well. Yeah, but we do evaluate, we do the uncertainty quantification only in the state space for this particular skill, but we can convert back into the global state space for the long horizon task.
If the skills are, you don't spend time. So when you're doing the joint maximize the overall Q values.
Yeah.
Doing the scaling is the Q function from each
I see. Yeah. Right. That I agree with you that this. Yeah. I don't remember that we had this issue because probably there's some normalization going on, but I'm not 100% sure right now. Yeah.
even if you share that we're all like general space
Yeah. Mhm. Yeah.
Yeah, and maybe a bit more general question. It appears that we can do much more things with time progressing in the abstract level of representations. You've repeatedly highlighted the importance also of the geometry in verifying all the actions. So what is your current opinion of how the two fit together, or where would you place like geometry in your world representation?
Yeah, that's a very good, that's always a question, right? Like where you make the split. I think PDDL Stream, for example, put it in the task planning, which is kind of interesting. But yeah, so so here, I mean, we basically did have the task planner only operate on the symbolic symbols, and then the policies and the planning is all in the geometric space, which I think makes task planning much more efficient, right? If you don't have this huge state space there. So that's why we split it in that way. But I can see that there are some, some scenarios where you might actually want to have like some geometric information in the task planning as well, right? But it should probably still be maybe some not massive state space there. So it's a question of efficiency and expressivity. Is that a word? Yeah. So so I don't know. It depends really on the task, I think. So, but this is like not an easy question to answer in general, I think. Does that answer your question? Actually, probably not. It's like a gray answer. Yeah.
So I'm curious about combinatorial generalization of this sort of pipeline. So it seems clear that the LLM, seems clear that the task planner. So I'm a little worried that possible the Q function representation of the task part that if you haven't seen, it seems like you have to choose a representation for that would provide a similar, a reasonable function, even if I haven't seen a yellow cube on top of the whatever. Are you doing that now? Or is that a bottleneck in the sort of generalization?
Yeah. I mean, so for sure. So for example, again, as I said, with tabs, we're using policies that are single step. We actually treat them as banded for now, right? Like just to focus on the planning part with learned policies, we just simplified that part. So it's actually a banded. And we feed it this low dimensional state that contains this geometric information of where all the objects are and so on. But Concept to Robot, as an example, and many other works, they use an RGB image as input. And then Concept to Robot actually is also formulated as a banded. But there are many works that have like a model-free policy, right? That is a feedback policy, basically. And how to plan with those and with these large input spaces. Yeah, I'm not sure. You need like huge amount of training data there, right? And so I think so that's the question of the input representation that I also don't have an answer to. Again, we simplified it a lot here in these works where we just said we have some vision system that provides us at least with a noisy pose of the objects. And we assume the objects are known, right? We have maybe a model of it in some form. While on the other end, people are just using RGB images, right? And I'm wondering what is there in the middle that keeps our input state space low dimensional, but maybe also interpretable, so that we can feed it directly into the LMM as one use case of why this should be interpretable, right? But I don't yet see, or please tell me, like, what's the latest, greatest CVPR work that gives me object poses with reasonable noise for arbitrary objects. Yeah, I know. No, I would love to hear like, what is a object perception system, even taking RGBD input, right? That gives me reasonable, just object-centric output, right? That could be an input to this, a low dimensional input to this policy. Don't know. Love to hear. Yeah.
So for the symbolic planning, I think PDDL is widely used. But I think also the temporal logic stuff, LTL and STL are also widely used.
Yeah.
I think for the long horizon, for example, if the two subtasks are will influence each other, they are coupled, and then the logical structure will be considered. So I wonder what's your opinion about the STL-based planning?
Yeah.
DDL-based planning.
I know very little about it, so I don't quite understand LTL, for example. I don't understand it well enough at all to make an informed guess. I find it really interesting to explore that direction though, because I think it's of course way more expensive. And so what would that mean, for example, for the labeling of these videos, if you would not describe it with these simple pre and post conditions and you solve it as a temporarily extended action somehow, right? Like, what else could you get out of there? Yeah, so I know too little about LTL to answer your question, but I would love to learn more about it actually. Yeah.
Thanks again, Jeannette, for giving such a great talk and answering all these questions. If there are any other questions, maybe can just follow up afterwards. But yeah, let's for now, thanks everyone for coming again. And again, thanks again for Jeannette for giving this.